Hello everyone, thank you so much for watching our talk. My name is Amine and this is a joint work with Desi, Georgia and Omar at MIT. Let us start by a motivating example. Consider the problem of personalized patient treatment where a patient comes to some healthcare facilities with given features, say vital, symptoms, demographic, really anything that informs us on the state of the patient. Then the patient is administered the treatment and then we observe an outcome. So if we look at this problem in the patient feature space, what's happening is the following. The patient starts in some state with some given feature. So this is represented by a point in this patient feature space. Then they're administered the treatment and then they transition to another state with different features. So some vitals would have changed, some symptoms, and this state is potentially associated to some outcome. So as a matter of fact, it is not really a one-step process, but it is a dynamic process when the patients, again, given their features, is administered a second treatment, and then a third, and their features and states keep evolving in this feature state space until we observe some outcome. And when we're dealing with these problems of personalized patient treatment, or in general, dynamic data-driven decision-making, what you observe is a sequence of paths. This is our data. A sequence of paths, features evolving with prescribed treatments and then some outcome. And the challenge and the goal is from these different paths to infer what is the optimal treatment or to predict counterfactual for some new set of features. So a new patient that arrives with features that are very likely never observed, as these are really continuous numbers. Think of blood pressure or medical history. What are the challenges here? The dynamics of how patients evolve under given treatments, how his exact features evolve given a specific treatment to the next set of features, are very complex. And in order to learn them, we would need very complex approximators, and typically we would use reinforcement learning techniques with neural networks and deep learning. But the problem here in healthcare applications and in general in high stakes applications is that using these complicated function approximators results in black box that cannot be used. A physician cannot rely completely on a black box algorithm to prescribe treatments. And therefore here interpretability is key and it is one of the main challenges in such complex decision-making tasks. So now the challenge is how do we bring interpretability to this problem to this dynamic data-driven decision-making problem. And the inspiration that we got to address this problem is from doctors actually make these kind of decisions. So this is a snippet of the guidelines for the management of arterial hypertension. This is managing the blood pressure. And they look something like that. So first, for every one of these guidelines, first some condition on the patient's features is stated. So think this is some decision tree shape where there's a condition on the age, it's between A and B, and then the blood pressure is within some range, and then there's some condition on the medical history. And this part of the feature space that is defined by these conditions is mapped to a specific treatment. So there's some notion of treatment groups, that the feature space is partitioned into some treatment groups. Now with that in mind, the idea is to use the data and to learn from the data a partition of this feature space that would constitute this notion of treatment groups. More precisely, these are states that would summarize the information we need to know about dynamic systems, and in particular would preserve the dynamics of these complex continuous state space systems, such that it suffices to know in which state the patient is to be able to predict how it would evolve under specific treatments, and also to know what outcomes would be expected. So more precisely, we want to map the parts of these partitions to states of a Markov decision process that would represent the system. So we start from this complex continuous state space dynamic systems on the right here, and then partition it to learn a reduced, discrete, more concise Markov decision process representation that summarizes the dynamics of this system. So in our work, we formalize rigorously this notion of a minimal representation, and prove theoretically that it is possible to learn the most concise representation of a dynamic system solely from observing transition data. And in particular, we introduce a practical algorithm that learns from data this concise representation, therefore providing interpretability to complex dynamic systems. This is our talk. Thank you so much for watching.